All right, I'm turning off my timer then because we're going to go for a longer period of time. No, I want to thank Konstantin. I want to thank Panos for organizing this session. What I want to talk about today is a little bit of a different topic. We're going to talk about using electrical measurements to characterize defects in 3D printed elements. And the thought process here, when you look at the elements, we intentionally designed them to have defects in them so that we could conduct the study. Right? So what I want to do is I want to spend some time talking about this. This is part of a much larger project. So we're looking at relatively small elements as we go through this process, but there's a joint project here with Princeton, and they're looking at larger elements, and the goal here is to develop techniques where we can scale these from one scale to the other. We have quite a few very excited students and postdocs working on this project because, as I mentioned, it's a combination between Oregon State and Princeton University. So the thought process here is, again, as I mentioned, we're doing this at a relatively small scale. So we've got the 3D printer. The use of 3D printing is growing. It's on the rise. And the question is, do we always get a uniform microstructure, a uniform mesostructure, a uniform structure of concrete? And if we don't, can we start to see what the role of defects might be when it comes to the transport properties in concrete? Now, I use transport properties because there are many different types of transport properties, and I'll start to describe these a little bit more on the next slide. So the basic idea here, right, is that many of the printing technologies that are out there are extrusions of filaments, and the thought process is those filaments get extruded and laid down next to each other. We believe that there is a film that goes around the outside edge of these filaments that tends to be more porous. It's a lubrication layer, and it's created by the flow of the material that comes out of the nozzle. We also know that these materials may not completely come together, and they may leave interfacial zones. So the question is, one, do these materials ideally fuse together? What happens if they don't, and can we detect it if they're not fusing together? So we have several different techniques that we're using to assess these transport properties. So here you could see a conceptual illustration. If we had some sort of fluid on this side, we would see an absorption into the material through the typical meso and micropores inside of the system, being absorbed into the gel pores and going in through capillary suction. But what we'd also notice is many times these interfaces allow preferential transport along them, and that allows us to reach higher degrees of saturation. Higher degrees of saturation would be synonymous with things like freezing and thawing damage or getting aggressive ions into the system faster than in other cases. So we're looking at absorption. We're also looking at permeation. So here the idea, and these are neutron radiography images, we actually pressurize the system where we have fluid on the top. We place it under pressure and we push that fluid through the system to the bottom. We also have cases where we look at absorption. Today I'm not going to talk about either the permeation or the absorption. I'm going to just talk about the role that electrical resistivity plays as a faster approach to measure some of these things. So here you can see several of these elements that are being printed. The basic idea here is we're going to change something called the extrusion multiplier. This is essentially the flow rate of the material coming out of the nozzle. So if we have a high extrusion multiplier, we're getting more material that's coming out than actually what's being laid down and being placed at a particular time. As we get to a lower number, we start to see that there's not as much material coming out. And what you can really see is when there's more material coming out, this kind of bulges and there's too much material there and it kind of overflows. If there's not enough material coming out, we frequently start to see gaps developing in these materials. Now, this is an extreme case going from way too pushed together to where we know we're going to have gaps in between the printed layers. So again, overextension, too much material is flowing out, so there's more material coming out the nozzle than what can be really placed effectively. And then under extrusion is when we have some of those gaps. Now what we're going to do is when these materials come out, we're actually going to start to measure the electrical properties of these. And here you're seeing the fact that we've got electrodes, we've got our conductive media, and we've got the elements placed in between those electrodes, and we're going to pass a current through that system. We're going to measure the resistance of the system, and we're going to convert that over to resistivity. So here you'll notice that the printed filament direction is perpendicular. Here it's in the length, the direction of the current. And again, here in the third direction, we have it shorter because it's only going to be printed about a ½ inch thick, and we're going to measure that as well. So perpendicular direction, parallel direction, and transverse direction. And we'll talk about the role that this plays. Now, in most classic concrete materials, we don't talk about directionality, but in the printed materials, we definitely have to do that. So again, just to spend a couple seconds on the electrical part of this, the idea here is we're simply going to use Ohm's law, where we have voltage is equal to the current times the resistance, right? We measure the resistance, and then we correct for that to come to conductivity or resistivity. So I'll use both of those terms interchangeably, right? But the real importance of this is used very frequently as a fast assessment, the RCPT test, the resistivity test. It's a fast measurement of the transport properties of our overall system. Now, what we're actually measuring when we look at this, right, there are really three phases in the system that we're looking at, right? We can look at the vapor phase, we can look at the solid phase, or we can look at the fluid phase. The vapor phase is these air pockets or vapor-filled pockets that might be inside of the system. They have a conductivity that is incredibly low. They're very difficult to conduct electricity through. Our solid phases, whether it's the solid cement or whether it's an aggregate, again, have a very, very low conductivity. The phases that really are the ones that are responsible for transport are the fluid phases inside of the system, right? It's not pure water. It's water that has ions in it, right? And that's the one that is actually 10 orders of magnitude more conductive. So if you actually model all of these phases, it always comes down that it's the pore fluid that's the conductive phase that's inside of the system. Now, if we look at this and we start to either look at a diffusion concept or a resistivity concept, we can look at either a series model, a parallel model, or a modified model, where the diffusion coefficient is going to be equal to the diffusion coefficient times the porosity, diffusion coefficient times the porosity. And if we look at this, we don't really have this case most of the time. We don't really have this case most of the time. So what we end up with is either a diffusion coefficient or a conductivity or a resistivity that is based on the conduction or the resistivity of each phase times the volume fraction or the porosity of that phase. And we put in this term that we refer to as beta, which is essentially a connectivity term, right? If it's a 0, we end up back in the series case. If it's a 1, we end up back in the parallel case. So beta is always between 0 and 1, and it's a descriptor to try to talk about how wiggly the pores are, how connected the pores are, and how much these pores kind of neck down. So if you had a great big pore connected from one side to the other, we have a connectivity of 1. If we have a pore that's not connected to anything, it has a 0, and anything that's wiggly like this, we see that number starts to decrease. So again, as we start to look at this, we're going to measure these resistivity properties, and then we're going to start to perform some of these calculations and look at those calculations and try to interpret what's happening. So here's the majority of the data that I'm going to share is just the formation factor or the resistivity that we're measuring this system. And as we look at this, if we look at the overlap between the filaments, right, so this is that one with the high extrusion multiplier where the system is kind of bulging. Here is one where it's kind of low and the system doesn't have enough material coming out. If we look in the three directions, we can see that they are impacted by that same porosity very differently. Right, the one direction here has about a 15 or a 20% reduction, right, where the second and the third direction coming out of the screen have a much more substantial impact, all right, of the connection of or disconnection of these filaments to each other. So the first thing that we really need to notice here is the behavior, as we might expect, is very anisotropic. Right? It depends on the direction that we're looking at this. And that makes sense because we're trying to align those extruded elements with each other. So as we look into this, we want to get an assessment of what that porosity starts to look like. So we've applied microcomputer tomography to these samples. If you're really interested in the details, they're all provided here, and the information is up on the website. But the basic thing that we're looking at is we're looking at the distribution of the porosity, and then we're going to start to try to calculate how connected that porosity is through the system. So we're going to essentially start to build a line on one side, connect that line to the other side, and see how connected that system is. And I'll show where that comes in a few seconds. But this is simply a three-dimensional, this is a slice of the three-dimensional element, looking at that slice in three different directions. So we looked at it in direction 1, where the printed elements are going in top to bottom. Direction 2, right, again, we see these printed elements and we see these gaps. The gaps are showing up as dark. And direction 3 is kind of the height of the sample. And again, we're seeing some gaps starting to show up in the sample here, where the material is not being fully connected. Now, we can look at these images, and they're incredibly pretty images. People can turn them into different colors, but we can also turn them into actual data. And one of the things that we've tried to do is we've tried to come up with a simple way to represent this data so that we could start to look at it and we can start to use it. So one of the ways that we're doing this is we're going to break this up into each voxel in one direction, and then we're going to calculate the percentage of that voxel that's a pore and the percentage of that voxel that is a solid, right? So if you think about it, we're going to take little tiny elements from one side to the other and simply measure how much is connected and how much is open inside of that system. So when we do that, we can come up with these distributions of the void space, and they start to look like these plots that we're seeing here. So if we had, on the bottom we have 0, this means the material is a complete solid. At the top we have 100%, this means it's a straw from one side to the other, it's completely porous. And then we have the cumulative frequency plotted along the bottom axis. So as we look at this, we have a very small portion, right, maybe 15, 20% of the material that is completely solidly connected from one side to the other. As we start to move up, we start to see that we have a smaller version of these, a small number of these pores that can get connected from one side to the other. Now the real takeaway on this is the distribution of these pores, or the distribution of these holes, depends substantially on the printing direction that we have. In the one direction, what we notice is all three of these have the same overall porosity, right? Because the solid has the same overall porosity. It's really the directionality of the printing that leads to how that porosity is connected from one side to the other. So in the one direction, what we notice is we have a lot of pores, but there's only about 20% of that being connected from one side to the other. 20% of the straw is open, the other part is solid. When we start to look at the other directions, the 2 and the 3 direction, up and down direction, and the direction along the fibers, we start to see we now introduce pores that are much more connected from one side to the other. And this is going to make a big difference, as we might expect in the transport properties, because it's much easier to go through a long pore that is really connected than to have to go through a series of smaller pores as we work our way through this. So now we can start to convert this over into an example analog, and we do this quite frequently, where we take that pore that we had and we start to break it up into pieces. And we have a piece that's solid, a piece that's a pore, a piece that's solid, a piece that's a pore, a piece that's solid. So we might be representing this piece right here that we can see visually, right? And we can start to build that together using equivalent circuit modeling. So the simple concept here is we're going to have a circuit that starts to measure the paste and the solid together, right? We can add the resistances together, and we know that there are rules. If we go back to our electrical engineering classes, there are rules for how we do this. Now, the one interesting piece to these rules is it really doesn't matter if the solids are all connected and then we have the porosity, or they're distributed like we see here. It doesn't matter what order they come in. It just matters that we get the volume proportions of these right. We can then start to sum all of these voxels up across the entire sample, right? And here I've shown 3, but we're doing something like 30,000 of these when we look at putting the 3D image back together. And we can, again, now determine the equivalent resistance of the overall sample. So when we do this, what I want to point out are a couple conceptual illustrations and then show you what the data really looks like. The first one I'm going to talk about is when we have this distribution of porosity. where all the porosity is essentially short disconnected pores, right? This is that case that we saw where we have the same amount of porosity, but essentially they're short pores, and there's only about 15% of them being connected across the entire system. And when we do that, we effectively have a relatively constant drop-off in the resistivity, and this is due to the dilution effect. This is simply the law of mixtures, right? This is along the lines of what we expect. If we take that exact same porosity and we distribute it differently in this sample, we say that there's a small number of pores where the porosity is connected from one side to the other. The impact on the resistivity is much more dramatic, right? So here the takeaway is the more connected the porosity is, the bigger the impact we're going to have on our overall measured properties. So again, this is illustrating that it's important that we understand that we have an anisotropic material, and just mentioning a single number like an RCPT number for a printed material may not be sufficient. We have to look at this in three directions. All right? Now, we can also, instead of having this ridiculous case where all the porosity is the same size or all the porosity is connected from one side to the other, we can actually start having some sort of a gradient in that porosity and start describing the overall behavior. And if we start to just describe this slope, we can really see that we're connecting those points from one side to the other. And the idea is once we get to a significant slope here, once we start to see a significant number of these larger connected pores from one side to the other, we see that that makes a major impact on the overall conduction or the overall resistance in the sample. So now we have a working model and a working concept. Let's apply it back to the samples that we have. In the one direction, right, so where we're going across the filaments, we actually predict this behavior incredibly well, right? And that's probably not really surprising. Right? In the 2 and the 3 direction, we see that there's something that we're not able to capture in the predicted solid line. Right? We're seeing that there is something that we're not able to capture here. And the real thing that we're not capturing with this simple model is the fact that they're connected out of plane. Right? So that's one of the things that we have to work on with this simple model is the out of plane connection. So you can think of that as I have a straw here and I have a straw below it, and somehow those two straws are working in tandem with each other. So the simple workaround, at least for the beginning of how we deal with this and deal with this out of plane version, is to change the connectivity factor, all right, depending upon the orientation that we're looking at the sample. So our connectivity factor, when we are going across the filaments, we can leave that as a value of 1, all right, and simply use the connectivity that we would have from our sample. But when we start to look at this idea of this out of plane, we have to drop that down to a 0.5, essentially in the 2 direction, where we're starting to see these large gaps opening up, because those large gaps are more likely to be connected out of the plane. So this seems logical that these large pores are going to be connected in the filaments and across the filaments. We can actually use the tomography images to calculate that out of plane connectedness. Right, but what we're trying to do is come up with simple rules that we could apply without having to do tomography on every single specimen that we're trying to measure. So in summary, the electrical resistivity of 3D printed elements has been measured for several systems where we've intentionally introduced printing defects. The formation factor, or the resistivity, has been measured in these 3 orthogonal directions. We know the materials are not isotropic, and we have to start treating them anisotropically. We see that the equivalent circuit model is useful related to the oriented porosity because we can detect the change in resistivity. What we really are doing well is predicting when we have small disconnected pores. What we're struggling with that simple model is when we have connected pores in 3 dimensions, and what we're doing currently is we're essentially introducing a factor to the connectivity, but we'd like to be able to relate that back to essentially looking at the tomographic distribution of those, but come up with some simple rules with that.